Hi, everybody. I'm Dario. I'm very sorry I cannot be there in person, but I am actually teaching at the moment. And before diving into the presentation, I would like to thank the funder for all the work that I've been doing in the last years, the RFU Injury Player Foundation, and the EPSRC through the Camera Project, and all my collaborators. My talk today is focused on tackling, in fact, and as a biomechanist and injury prevention researcher, unfortunately, I'm very interested in this topic because 40% of all catastrophic injuries in rugby are related to tackles or scrums. So we ought to do something about it in order to make the game safer. And if you are an injury prevention researcher, you do know this cycle very well. And also, if you are a biomechanist, what you can do in relation to the van Mechelen cycle is to work during step number 2, so understanding what are the causes or the injury mechanisms, so that we can provide some information and ideas for prevention that other people will test as well in the real world. But what do we know about the causes and tackling in general from a biomechanical perspective? Loads of work has been done, but I don't think we know enough about it. So there are many observational studies or video analysis studies, which are very important to flag up the risk factors. But here is missing a bit the causal link between injury and technique or internal loading. Also, the same problem is with personal reports, and more kind of advanced biomechanical analysis included kinematic and kinetic analysis, but most of them were carried out in very controlled environment like the lab, so the ecological validity is not there. Also, recently the focus has been mainly on concussion. So to me, there is still an open debate. And there is an open question that was actually posed very wisely by Dennison et al. Actually 10 years ago, and which is related to what's the injury mechanism related to tackle? Is hyperflexion or buckling? This was the duel that was kind of highlighted by Dennison, and so far nobody has kind of ever managed to truly answer that question, because it's really difficult to understand what's the link between the sternal load that we can measure or the technique that we can see during an actual tackle to the internal load experienced at the cervical spine level. So the aim of my talk today and the project I'm showing you aim to identify the most likely injury mechanism during rugby tackles. And once we've done that, we wanted to provide some key kind of messages and inform injury prevention strategies based on such knowledge. But how do we do that? Well, in this slide, I'm presenting you the approach that myself and my group have embraced in the last 7 years. And the main idea is that you want to be able to replicate as much as you can what's happening in the real world. And we're talking about replicating non-injurious event, which can be actually quite well replicated in the lab. And that will involve in vivo tests on rugby players. And that allows you to get a very good understanding on what's the technique using during tackle, how rugby players are activating spinal muscles during tackling. And you can also add some musculoskeletal models on top of this analysis in order to estimate what's the internal load experienced during non-injurious event. However, what we want to do actually is to understand what's happening during an injury. So we do miss the other bit, which is the actual injurious event analysis. And this can be done, as you might already understand, only using in vitro tests. So you can apply the same injurious load onto animal tissue, like specimen, like porcine specimen or anthropometric tested device, and that will allow you to really measure very accurately the external load during injurious event, and also the tissue strain, as you can see in this video here. But the final step that actually brings everything together is the use of computer simulation that allows you to generate new kinematics, new injurious kinematics, based on information coming from experimental tests. So, for example, you can use this musculoskeletal model in a forward dynamics mode, which means creating new kinematics. And you can make this model start at a specific position, make this muscle activating as the rugby players activate the muscles, apply a specific force on the head, and generate the injury. This is the approach that we use. And then you run the simulations, that's it. And how do we set up the design of this kind of big batch processing of simulations? Well, what we wanted to do, we wanted to explore different scenarios. And to explore different scenarios, we run about 2,000 simulations there. And that number is made up by essentially the number of neck angle conditions that we used, 177. And the other kind of condition that we used to set up the simulation. So this is a schematic of the simulation, where you can see we modeled the ball carrier as a set of 2 spheres here. We can discuss it later. But long story short, less is more. So these kind of spheres are used to create what we call the contact model. The contact model is a model that allows to generate and estimate forces when 2 or more solids or ellipsoids or spheres are penetrating into each other. And that's the reason why we put another sphere here on the skull, so that when there is contact between this kind of bodies, we get out a force. And the ball carrier had an initial kind of speed as well, and the torso angle was kept constant in that sense. But we changed the tackler approaching speed onto before the contact. We had a high speed and a low speed, and we also changed the trunk angle of the tackler as well. So these are the main variables that we used, and these are the variables that we used to explore different scenarios. Here, there is an example of a simulation, top view, where the tackler is now in contact with the ball carrier. There is force generated by the contact model. As you can see, this force is transmitted onto the skull and the model, and the cervical spine is loaded with force and moving accordingly. There are some muscle activation there as well, but that's to give you an idea of what kind of simulation we are talking about. Right, what did we find out? So the very first take-home message, analyzing all the different simulation that we run, is that head down is bad. So neck flexion angle actually had the largest effect on neck loading. Potentially, if you are a rugby coach, that's not in use for you. I believe that from a biomechanical perspective, I was very pleased to see that. But I can give you an explanation on why, from a biomechanical perspective, this is true. So if you see the normal kind of position of the spine and the position of the spine in more flex position, in a more flex condition, you can see that in a more flex condition, the cervical spine loses its natural lordosis, which is this kind of curvature. And that makes the spine very much aligned with the force applied onto it, or more aligned. And from a biomechanical perspective, when you lose this kind of lordosis, the spine becomes much stiffer, because when you apply the force, the spine cannot move much from there, whilst with the lordosis, the lordosis will allow more movement and therefore dissipation of the force. Whilst when the spine is completely straight, the force is transmitted across all the vertebrae, and much more compressive load is transmitted onto the spine, rather than dissipated through movement. From a more scientific perspective, if you want to see some data, what you can see here is the joint reaction forces, the compressive one, and how these kind of compressive forces were changing across flexion extension. So this is flexion is negative, extension is positive. So head down is here, head up is here, lateral bending, and axial rotation. And you can see straight away that actually the only neck movement that had a large effect on the neck loading was flexion extension, because the lateral bending, lateral rotation did not have any effect on the loading. We see that kind of horizontal line there. Whilst if you look at the flexion extension, we do see there is a trend. And the trend is saying that the higher is the flexion, the higher is the compressive load. And it's very, clear that regardless the position of the initial kind of contact of the force, so if the force is applied posteriorly or centrally or anteriorly, you do see that there is a decrease in the compressive load whilst extending, so whilst moving with the head up. The second take-home message, which is truly exciting to me, is that we believe we could say that buckling is the main injury mechanism in rugby tackling. And that can be seen visually from this video, because if you try to compare what's happening to the spine during this video and what's the classic description of the behavior of the cervical spine during a buckling mechanism, where you see a flexion of the lower cervical spine and an extension of the mid or upper cervical spine. This is exactly what we see in this video. So this part of the spine, the lower part of the spine, is flexing a bit, whilst the other part is extending. This is actually backed up by data as well. So this graph is a bit busy, apologies for that, but what I'm showing you is the maximal joint reaction force during the simulation in compression, anterior posterior shear, and the flexion moment, a different type of initial loading condition, so posterior, central, anterior. And also I gave you a breakdown of how this kind of load was changing across different joints. The horizontal lines there are the injury threshold that have been kind of developed and found in the literature in the last probably 50 years. And some of them will be linked to a failure of the cervical spine, some of them to pain. But I put it there just to give you an idea of how close we are to this kind of injury threshold. But why we think that buckling is actually the mechanisms? But first of all, there is a classic buckling loading pattern where you have very high compressive load. Remember that with buckling, if you apply an axial load to the spine, what the spine is doing is having a kind of a C shape or a S shape. And when this kind of axial load becomes very high, the spine starts to buckle, in fact. And then, that's in fact due to the very high compressive load that we see here, and also a change of the shear forces across the spine, which is very kind of clear looking at the different joint levels here, especially for the central kind of condition, where some of the joints had a posterior and other anterior kind of shear force, which is again classic. It's a classic characteristic of buckling. The second reason is that related to the fact that peak compressive and shear forces do happen before reaching high flexion angles. So hyperflexion is mainly kind of due to reaching this kind of high flexion angles and having very high moments. However, we don't see very high moments here. We see mainly high compressive and shear forces. The third point is about the fact that regardless of what's happening towards the end of the injury, where you might see different type of neck position due to the fact that tackle is a very complex phenomenon, and the head can be kind of pocketed somewhere, and something very kind of complex can happen there. The very first injurious mechanism is the buckling one, and the injury happens due to this first mechanism. Finally, I would like to start a bit of a discussion with you in relation to the tackle height. In this graph, which is very similar to what you've seen before, we have included the max compressive and anterior posterior shear loading across different joints, so C3, C5, C7. And in this case, you can see there are 4 lines, and those lines are related to different tackle height. So the red, orange one will be more low tackling, so a low tackle, and the green ones are high tackle. And these kind of the dark and the light are changing with respect to the speed. So also tackling speed is included here. And looking at these curves, what is very clear is that, again, the neck flexion angle and the tackling speed are, at the time of impact, have got the largest effect on neck internal loading. So again, neck flexion, head up or head down is the main thing. And the speed has got, of course, as you can see here, a effect as well, which, this kind of curve is shifted down a bit due to the different speed, but we expected that because that's essentially physics. So the lower the speed, the lower the forces. But what about the trunk angle? So what about the tackle height? Well, that was quite difficult to see directly because of the large effect that the other variables had. But there is a way to answer that question from a statistical perspective. So we used a generalized linear mixed model to analyze the data across all the simulations. And that kind of generalized linear mixed model included as fixed factors the neck flexion extension, the lateral bending, the trunk angle, and the interaction between flexion extension and trunk angle effect. And as a random effect, we have the different joints. So what you can see here is the model, the output of the model, and how the model is predicted the joint reaction forces with different trunk flexion angle as an input. So what you can see towards the left is a very low tackle, towards the right a very high tackle. The predicted response and the variability of and the accuracy of the model is very high, and there is a clear kind of method there. So theoretically, with a lower tackle height, the risk to develop a cervical spine injury is higher according to this model. Right. So I would like to leave you with 5 discussion points potentially. The first one is related to the validity of this approach. I believe that we did as much as we could in order to make the simulation realistic and inform this kind of simulation with experimental data that we have. Second point is about the ability to predict spine injuries and flag up the most hazardous situation. So I think this kind of modeling approach can be used to do that. And the third point is about the fact that if the model is not seen as the first kind of to-go kind of approach, surely it can be used to inform the design of future experimental studies. So there might be some key questions that are coming out from the analysis of all the simulations, and therefore the model could be used also in that way. The fourth point is about the potential use of these models to support decision-making processes, mainly because you do see what's happening, you do see simulation visuals, you got some clues from the data, and some kind of decision could be informed by this. For example, the tackle height one, it's important to minimize the cervical spine injuries risk whilst also minimizing the concussion risk, for example. And the only way to do that is to understand what's the interaction between risk is to actually run a simulation, because otherwise it's impossible to do it and consider all the different factors at the same time. The final point is a bit of a teaser towards the future. And I would like really that this model could be used in real time on broadcast videos to provide support to the medical personnel and provide them with a kind of traffic light system where very kind of severe injury might be flagged up using this approach. Many thanks for your time, and hope to see you in the discussion, and thanks for your attention.